The 5 corrections are usually combined into one general equation which can be applied to any case where a measurement has to be converted into a horizontal distance. In this case, the surface distance AB has been measured as L. The angle of slope is theta, and the horizontal distance D is required. D equals L plus or minus the standardization correction, minus the slope correction, plus or minus the tension correction, plus or minus the temperature correction, minus the sag correction. For example, the surface distance along AB has been measured as 76.462 meters, and the angle of the slope was measured using a theodolite as 1 degree 25 minutes. The steel tape used had a nominal length of 20 meters and a standardized length of 20.011 meters at a temperature of 20 degrees C and a tension of 50 newtons. During the measurement, the tape was laid along the ground surface. Its temperature was 10 degrees C, and it was pulled at a tension of 70 newtons. The cross-sectional area of the tape is 1.9 square millimeters. The modulus of elasticity of the tape material is 200,000 newtons per square millimeter, and its coefficient of thermal expansion is 0.00000112 per degree C. The first step is to decide which corrections are necessary. In this case, the only one that does not apply is the sag correction, because the tape was laid along the ground surface. The other corrections are given by substituting into the relevant formulae. The standardization correction, the slope correction, the tension correction, the temperature correction. These are then used in the combined formula to give D equals L plus the standardization correction minus the slope correction plus the tension correction minus the temperature correction, which comes to 76.4761 meters, and this is rounded to the nearest millimeter to give the horizontal distance of AB as 76.476 meters. Tapes and chains can be awkward to use on some ground surfaces, and they can be time-consuming. An alternative is to measure the distance optically, where the measurement takes place indirectly above ground level and can be done in a shorter time. This is known as optical distance measurement, or ODM. Because of the widespread use of electromagnetic distance measuring instruments, only one ODM method is still generally in use. The reason that it has survived is due to the fact that it uses conventional surveying instruments. The technique is known as stadia tachyometry and involves the use of a theodolite and a leveling staff. Its main application is for the surveying of the positions of soft detail, such as trees, hedges, changes of slope, and so on, in order that they can be plotted on a plan. Consider the surveying of detail from a control point A. The theodolite is correctly leveled and centered over this point, and the leveling staff is held vertically at the point of detail being fixed, in this case a small bush. Once the theodolite is correctly set, and before any of the points of detail are fixed, an observation is taken to another control point, B. The horizontal circle is read and recorded. This establishes the orientation of the circle and is used later when plotting the detail points on the plan. Having established the orientation of the horizontal circle, the staff is sighted.
And you put the third section up, please, Roy.
And the person holding the staff keeps it as vertical as possible. It is not advisable to rock the staff as we do in leveling, since in stadia tachyometry it is read using all 3 hairs engraved on the diaphragm, and this is not easy to do if the staff is rocking. The top and bottom hairs are known as the stadia hairs, and give this technique its name. As a check, the middle hair reading should be equal to the mean of the stadia hair readings within 1 or 2 millimeters. The horizontal circle is read and booked. The vertical circle is read and booked. And a final check is made on the readings before the staff is signalled to move to the next point of detail.
Okay, Roy, can you move on to that tree over there, please?
When all the observations have been made, the orientation of the horizontal circle should be checked to ensure that it has not changed by resighting control point B. Finally, before moving the theodolite, the height of the trunnion axis above the known reduced level at control point A is taken. Consider an example where, with the theodolite at A and the staff at B, hair readings of 2.140 meters, 1.956 meters, and 1.774 meters are obtained, and the vertical angle, which is an angle of elevation, is measured as 2 degrees, 17 minutes, 27 seconds. From these readings, it is possible to calculate the horizontal distance d using the formula d equals ks cos squared theta plus c cos theta, where k is the multiplying constant for the theodolite being used, and c is its additive constant. Nowadays, these are invariably made to equal 100 and 0, respectively, by the manufacturers. S is the staff intercept and is equal to the difference between the top and bottom hair readings. So, substituting 100 for K and 0 for C gives D equals 100 S cos squared theta. And in this case, S equals 2.140 minus 1.774, which equals 0.366 meters. Therefore, D is equal to 100 times 0.366 times cos squared 2 degrees 17 minutes 27 seconds, which equals 36.542, which equals 36.5 meters. Remember, any reading error is multiplied by the K value of 100, so even a misreading of only 1 millimeter will cause a distance error of 100 millimeters. For this reason, any horizontal distances should only be quoted to the nearest 100 millimeters. Although it is only as accurate as synthetic taping, stadia tachyometry does have one big advantage in that it can also be used to measure the reduced levels of points. If the reduced level of A is known and the reduced level of B is required, then this can be obtained from the reduced level of B equals the reduced level of A plus HI plus or minus V minus M, where HI is the height of the theodolite trunnion axis above point A, V is the vertical component of the sloping distance, and M is the middle hair reading. The vertical component V is positive for angles of elevation and negative for angles of depression. In this case, it is positive, and it is obtained from V equals half Ks sine 2 theta plus C sine theta. As before, K is usually 100 and C is usually 0. Therefore, the formula simplifies to V equals 50 S sine 2 theta. And in this case, substituting for S and theta gives V equals 50 times 0.366 times sine 2 times 2 degrees 17 minutes 27 seconds, which equals 1.462 meters. So, if the reduced level of A is 111.43 meters, and the instrument is set up at a height of 1.51 meters above point A, then the reduced level of B is given by RLB equals 111.43 plus 1.51 plus 1.462 minus 1.956, which equals 112.446, which equals 112.45 meters. Because of the inaccuracies mentioned earlier, any reduced levels calculated by stadia tachyometry should only be quoted to the nearest 50 millimeters.